In this section, we will be looking at exponential and logarithmic equations. So there are different methods to solving these, and really you decide on the method that you need to use based on the information that you're given or how the equation looks in the beginning. So let me give you a quick, simpler example that will apply to number 1 and 2. Let's say I have 2 squared is equal to 2 to the x. The only way these can be equal is if the bases are equal, then the exponents have to be equal. So if the bases are both 2, that means that the exponents must be equal. So 2 equals x. So if you can have your equation, if you start with exponentials, if there is a way for you to make the bases be the same, then you can just ignore those and rewrite the equation with exponents only, because if the bases are the same, then the exponents must be the same as well. So if we look at number 1, we could hopefully agree that the base is the same on both sides. We have we have one base on the left and one base on the right. They're both 4. So since those are the same, we can simply write an equation with the exponents set equal to one another and solve that. So that means 3v minus 2 must equal negative 8. And now that's much simpler to solve. That's just a linear equation. So we're going to add 2 to both sides. So we will have 3v is equal to negative 6. Then we need to divide by 3. And so v equals negative 2. Okay, if you want to check your work, you can. You can plug in the negative 2 for the v, and you will see that you get 4 to the negative 8 equals 4 to the negative 8. There's your answer. Okay, so number 2. Same direction, solve. So we have one base on each side. On the left-hand side, we have 81 as the base, and on the right-hand side, we have 27 as the base. Those are not the same. However, look to see if both of these can be rewritten in the same base. So in other words, 81 is 3 to the 4th power. 27 is 3 to the 3rd power. So I could rewrite those in that way. So 81 is 3 to the 4th. Then I just bring down the other exponents that were there. 27 is 3 cubed. Bring down the other exponents that were there. If you have one base and then 2 exponents like you do here, remember that what you do is you multiply the exponents together. So in the first case, you distribute the 4. So we'll get 3 to the negative 4x minus 8. And on the right-hand side, we multiply 3 times 5x, and so we'll get 15x. Since we now have the bases the same, we ignore the bases and simply write an equation with the exponents only and solve. So now we have negative 4x minus 8 equals 15x. So add, whoops, not 8 this time because we have an x on both sides. So we're combining our x's. We'll add 4 to both sides. So that will be negative 8 is equal to 19x. And then to get the x by itself, we divide by 19. So x equals negative 8 over 19. Number 3, solve. So this one we have exponentials on both sides, but not the same base. 1 over 64 is not the same as 2. We could write it in the same base though. If we notice or know that 64 is 2 to the 6th, we could write that as 1 over 2 to the 6th to the 3n is equal to 2 to the 6th. Okay, and so now if you remember, if you have a positive exponent, you can change it to a negative by flipping it over the fraction bar. Usually you try to make it positive, but in this case, since we want the base to be 2, I need to make this 1/2 into a 2. And to do that, you just change the sign on the exponent. So this 2 to the 6 is the same as 2 to the negative 6. Okay, so then we have that. Again, we can multiply our exponents, so that would be 2 to the negative 18n is equal to 2 to the 6th. And now you can see we have the same base. So we ignore the base and we write the equation with exponents only. When we divide by negative 18, we will get the n by itself, and you will see that n is equal to negative 1/3. So 1, 2, and 3, the approach here was to make the base be the same so that we could ignore the base and write the equation with the exponents only. All right, so number 9, same directions, it just says solve. So now I have, first of all, the left-hand side is the only one that has an exponent. The right-hand side does not, so that's different. Also, 9 and 1. There is no way we can make this be the same base. 9 is 3 squared, but there's no way to make the 1 turn into a 3 or 9. So what we're going to do here is we're going to notice that only one side has an exponent. This is a great example of when you can just change to logarithmic form and see if that's helpful. So when we want to change to logarithmic form, remember we identify the base. So we're going to have log base 9, we go across the equal sign, of 1 is equal to x minus 10. I really don't need those parentheses, so let me write it without, x minus 10. And now, hopefully you can see it's easy to solve for x. To get the x by itself, all we have to do is add 10. So we will have log base 9 of 1 plus 10. So here, whoops, here I'm adding 10 to both sides. Okay, so 10, you can't just add it to the 1 because the 1 is what you're taking a log of. So it's just going to be a plus 10 is equal to x. Now you would try to simplify. So log base 9 of 1, anytime you're taking a log of 1, that's always 0. So the log of 1 is always 0. So this would be 0 plus 10 is equal to x. So that means x is 10. And that would be your solution. All right, so again, if you have one side that has an exponent and one side is just a plain number, you can just change to logarithmic form and see if that helps you. So number 5, this one looks way more complicated, but I do see that I only have one thing that has an exponent. If I can get that, the e to the negative 5x minus 2 by itself, then I would have a form like number 4. So I think I can do that. If I add 4 to both sides, that would help my case here. So I would have 8e to the negative 5x minus 2 is equal to, that would be negative 86. Again, I'm trying to get the e raised to the power by itself. So I want to get rid of this 8. So since it's multiplication, I'm going to divide. Okay, so that'll give me e to the negative 5x minus 2 is equal to, well, this would reduce to, let's see, negative 43 over 4. And now you can see that I have the e to a power by itself and then just a number on the right. So this is when you want to change to logarithmic form. So identify the base. The base is e. Since the base is e, we want to use natural log. So it'll be the natural log base e of negative 43 over 4 is equal to negative 5x minus 2. Whenever you're solving problems here, you want to kind of pay attention when you have a log or natural log, what you're taking the log of. So here, I'm trying to take the natural log of a negative 43 over 4. If you put that in your calculator, you will see that you get an error. That's because you can't take the log of a negative number. So this breaks down right here. There's nothing you can do. So this is no solution. And if you didn't see it at this point, That's okay, because let me go over here to the right and show you what would happen. You would have the natural log of negative 43 over 4 is equal to negative 5x minus 2. So you would add 2 to both sides. Divide by negative 5. And then you would get x. And so in order to really tell what x is, you would put that in the calculator and try to reduce that. Again, you will see that you get an error because of the negative, what you're trying to take the log of. So no solution here. All right, number 6. All right, so the first choice we have is to see if we can get the bases to be the same. Well, that's not possible in this case. 3 and 7, we can't get them to be the same base. The next possibility is if only one side has an exponent, then we could rewrite it in log form, and it's pretty simple from there. That is not the case here because they both have exponents. So in this case, what you're going to have to do is you're going to take the log of both sides. So you're going to take the log of the left and the log of the right. So you're taking the log of both sides. It's just like square rooting both sides or adding 5 to both sides. You're doing some operation to both sides. Here we're taking the log of both sides. Now what you want to do is you want to use the power rule. So we learned that in the previous section, where you can take the exponent and bring it down in front of the log. I'm going to do that to both sides. Okay, so now that'll give me 2x plus 1 times the log of 3, and then x minus 2 times the log of 7. Okay, so now we're at a good point where we at least have the variables down as a, not an exponent. So now what we have to do is try to solve for x. But notice that we have an x on both sides. Before we can start moving stuff, we need to distribute. So that means we need to distribute this log of 3 to both of those pieces and the log of 7 to both of those pieces. So this is going to be 2x times the log of 3 plus 1 times the log of 3. And that's going to be equal to x times the log of 7 minus 2 times the log of 7. Okay, so now anything that has an x, you're going to move to the left, and anything without an x, you're going to move to the right, because I'm trying to get all my x's together. So if it has an x, like this one, I'm going to move it to the left. Okay, so it crosses out on the right-hand side. If it does not have an x, I'm going to move it to the right. So now I will have this crossing off. So you can see I have two pieces on the left now. I have the 2x times the log of 3 minus x times the log of 7. And on the right-hand side, I have a negative 2 log of 7 minus log of 3. So since everything on the left-hand side has an x in it, I can factor that out. And that's what you want to do here. That's why you move everything with an x to the left, so that you can factor it out and get a single x. So if I factor out an x, that means I'm dividing that out. So I'll have 2 log of 3 minus log of 7, because I'm dividing out the x, is equal to negative 2 log of 7 minus log of 3. Okay, last step to get the x by itself. We have x times all of this in parentheses. So we're going to divide both sides by everything in those parentheses. So 2 log 3 minus log 7 on both sides. So 2 log 3 minus log 7. Okay, so that gets the x by itself. Okay, So now we have x equals, and then you can use your calculator to give an approximate answer. This would be your exact answer, but go ahead and give an approximation to, let's say, 3 decimals. So we will have, when you put this in your calculator, you should get negative 19.857. So to the nearest thousandth place, there you go. So you can see that in this case, this is a lot more work than those first 5. So this is one of the lengthier processes. Okay, now in number 7, so in all of those that we did above, they're all exponentials. They're exponential equations that we're solving. You can see in number 7 it's different. Now we have a logarithmic equation, because it's starting with a log, that we want to solve here. So one of the things you can try to do is first try to see if you only have one log, if you can get the log by itself, and then rewrite it in exponential form. So here we could do that. If I divide by this negative 8, so divide both sides by negative 8, I will see that I get log base 9 of x is equal to negative 2. And then I can rewrite it in exponential form. So first identify the base, and then go back and forth across the equal sign. So it's base 9 raised to this negative second power is equal to x. And so this would just be 1 over 9 squared, which is 1 over 81. Now, before I say, oh yes, this is an answer, I have to check it. If you're starting with a logarithmic equation, you have to make sure that whatever you're taking the log of is positive. So what I'm going to do is whatever I have here, that has to be greater than 0. It has to be positive. So my answer I'm going to plug in here and see if that's true. Is 1 over 81 greater than 0? Yes, it is. That means that this is a valid solution. In example 8, again, we're starting with a logarithmic equation. Remember in the exponential equations, if I could get one base on each side and they were the same, I could ignore those and just write an equation with the exponents. Here, if I have one log on each side of the equal sign and they're the same base, I can ignore that and just write an equation with what I'm taking the log of. So since these are both natural logs with a base e, I can rewrite this equation simply as 10 minus 3x is equal to negative 4x. And so to solve, I would add 3x to both sides. I would get 10 is equal to negative x. Divide by negative 1. So x equals 10. Okay, to check, everywhere I have a natural log, I have to plug that in and see if it's going to give me a true statement. So first I'll check this one, the first one. So 10 minus 3x has to be greater than 0. I'm going to plug in my solution. Oh, whoops, how did I miss the negative? This is supposed to be a negative 10, so that changes things. This should be a negative 10. Okay, so 10, this will be plus 30, which is 40. 40 is greater than 0, so that checks. Now I want to check the second one. So I have the natural log of a negative 4. So negative 4x has to be greater than 0. I'm going to plug in my x, which is negative 10. Negative 4 times negative 10 is positive 40. Is 40 greater than 0? Yes. So since it checks, let me just rewrite it so the negative is clear. Our answer is, in fact, negative 10. Number 9. So we really would like to have one log on each side, and then we could ignore the log. Notice all of these have the same base. They're all understood to be log base 10. Remember in a previous section, we had rules that we could use to expand or condense logarithmics if they had the same base. And so on the left-hand side, these are both base 10, and it's subtract, so I could actually combine these into a quotient. So I could rewrite this as the log x plus 3 over x is equal to the log of 74. And so now this gets me where I want to be. Since I have logs on both sides, one log on both sides, I can ignore those and just rewrite the equation with what I was taking the log of. And now I'm going to solve. So first I need to get rid of the x on the denominator, so I'm going to multiply both sides by x. So that will give me x plus 3 is equal to 74x. Subtract x from both sides so I can gather those together. So I have 3 equals 73x, and then divide by 73. And so we have x equals 3 over 73. Again, I need to check. So I've got a couple of them to check here. Here I'm taking the log of x plus 3. X plus 3 has to be greater than 0. If I plug my number in for x, is this a true statement? Yes, it is. That's still positive. Next, I have the log of x. So x has to be greater than 0. Well, 3 over 73 is positive, so it's greater than 0. And then last, I have the log of 74. Well, there's no variable there, so there's nothing to check. So this is a valid solution, 3 over 73. So the last example I want to share with you is this one, number 10. Again, we really want to have one log on each side of the equal sign. On the left-hand side, these are both natural logs base e, so I can combine them. Since it's a plus, this is going to be a product. So this would be the natural log of x times x minus 3 is equal to the natural log of 7x. So this would be the natural log of x squared minus 3x, I'm just distributing here, right, is equal to ln 7x. Okay, so since I have a natural log on both sides, only one, I can ignore those and rewrite the equation with just what I'm taking the log of. So x squared minus 3x is equal to 7x. Now I want to make all of my terms be on the left-hand side, or just one side of the equal sign, and set it equal to 0, because this is a quadratic equation. So I'm going to subtract 7x from both sides, and I will get x squared minus 10x is equal to 0. So now you have a quadratic. You can do a couple of different things. Probably the easiest would be to factor. So I have an x in common. If I factor out an x, I get x minus 10 left. And so now I can set each factor equal to 0 separately and solve. So x equals 0 is one possible solution, and then x equals 10 is another possible solution. You have to check both of these in all scenarios. So let's start by checking the 0. So I have ln of x. So x must be greater than 0. If I plug in 0, that's not true. 0 is not greater than 0. So this is not a valid solution. I can rule it out automatically from the very first one. If it doesn't work in one, it's not going to work at all. So now I want to check the 10. So again, x has to be greater than 0. If I plug in 10 here, that does check. 10 is greater than 0. Now I want to check the next one. X minus 3 has to be greater than 0. If I plug in 10, I have 10 minus 3, which is 7, and 7 is also greater than 0, so that checks. And then last I have 7x. So 7x has to be greater than 0. I'm going to plug in my 10. That's 70. 70 is also greater than 0, so 10 checks all the way down the list, so that is my solution.